Swayam Prabha. Digital India. Educated India.
Okay, I think we should get started in the interest of time. I know people are maybe finishing tea and they'll just walk over shortly. So welcome to this second parallel session. So this session is on carbon capture and utilization. And you would have noticed that there are three sessions. This is first of the three sessions, and that probably conveys how important this topic is. And the session chair. So we have three presentations. We have two contributed talks to begin with, and we'll finish with a keynote talk at the end. So let's get started with the first talk. So the first talk is coming from, the topic is again, as you can see, is comparison of the performance of CO2 separation from gas wells using cryogenic distillation and controlled freeze zone. And the presenter for the talk is Renanto. So I request the presenter to kindly begin.
Very much. Ladies and gentlemen, my name is Renato, and I will present work that has been done by my student, Ms. Vivianti. The title of this work is a comparison of the performance on CO2 inspiration for methanol as well, using cryogenic distillation control. The background is we know that the greenhouse gas emissions by source can increase the temperature of the atmosphere, and the sources can come from nitrous oxide, fluorinated gases such as carbon dioxide also here. And the greenhouse effect, we know that the energy from the sun warms the earth and some escapes back to the space. And we are concerning on the CO2 emission. The technology now to reduce the CO2 emissions is by capturing the CO2 either from the industrial plant or from the oil and gas well, where we know that we have also CO2 in gases. And the capture is to remove CO2 from the source and transport CO2 to some sink and then storage, inject CO2 into a reservoir of rock formation, and sometimes also can be in the aquifer. And some of the biggest plant in the United States, WA Paris, it is the electric plant, power plant, where they use the flue gas with CO2, okay? And then they capture the CO2 system, and 90% of CO2 free processed flue gas. And we put the CO2 also, we can utilize it for enhanced oil recovery. And then some of the CO2 also comes out with the oil, and the CO2 can be returned to inject to the formation. And this is the gas well in Natuna Island, where the composition of the CO2 over there is about 71%, which is unusual because mostly in other area in Indonesia, the CO2 is just around 30 or 35%. And we studied this for the separation of CO2 from hydrocarbon is using cryogenic. Because if you look at the data here from Palma et al. 2021, the comparison of N activities here for various carbon, you can see that the cryogenic distillation has about the energy duty of 1.47 million joule per kilogram CO2. Okay, so if you look at the table here, this is the highest energy duty for removing CO2. And using CO2 spiration technologies, we can use some processes like absorption, calcium looping, and we have cryogenic, membrane, and biological with microalgae. And cryogenic distillation technology, according to Palma 2021, cryogenic or low temperature spiration, it has conventional and unconventional method. In the conventional, for vapor liquid, we have the cryogenic distillation, which is conventional. And for the unconventional, we can have cryogenic liquid, with exchangers and packed bed. And this is the cryogenic distillation that is given by Yosef et al. In 2018. And you see there will be two columns usually for cryogenic distillation to separate the hydrocarbon from CO2. And the CO2 here comes out as a liquid gas. And for controlled free zone, it has been worked by Valencia in 2012 using one column, as you can see here, which has the conventional distillation or rectifying part at the top and stripping at the bottom, and in between is the controlled free zone in order that the temperature of CO2 can be obtained as liquid. And this is the operating condition in the feed stream for that has been worked by Nizam in 2022. We use this data to compare for the CFZ and cryogenic distillation. And this is the result for discussion. The cryogenic distillation, we have the same operation just like for CFC with pressure 38 bar, string number 20, and the reflux ratio of 0.78. And for the CFC, we also have this specification. As you can see from the table, we use the same CFC condition in the CFC. And for the controlled free zone in the Aspen Plus, since there is no palette for CFC, we use a flash operation. And the result, we can see here that the purity using cryogenic, I will say SCD, cryogenic distillation, which is 98.61%, and the CFC about 98.75%. So it's almost the same about the purity. However, from the recovery, we can see that cryogenic is only 92.65%, and the CFC about 93.16%. We compare those two, then we can see that the recovery of the CFC is much better than the cryogenic. And when we compare about the duty for its capture technology, we can have that the CFC has the heat duty of 0.8797 compared to the cryogenic of 0.6979. So the cryogenic distillation here has the energy, lower energy required compared to the CFC. And this is the result for having CO2 purity that can be used as the beverage carbonation, food processing, etc., and fuel production for methanol, formic acid, for CO2 injection to conventional methanol synthesis, and EOR, and then scope at the same. Conclusion, based on the simulation result using Aspen Plus, the CFC consumes energy 0.18 million joules per kilogram CO2, or 21% higher than cryogenic distillation. Though the CFC technology consumes higher energy, it has a purity of 0.14% and a recovery of 0.55% higher than cryogenic distillation. In other words, cryogenic distillation technology is able to obtain CO2 recovery and purity close to CFC technologies, so that it can be used for EOR or other utilization with lower energy consumption. I actually think that using CFC will be lower consumption. In fact, compared to cryogenic distillation, that CFC has higher energy consumption to get purity, high purity of CO2 and high recovery of CO2. I think that's the end of my presentation. You have some questions I'd like to answer.
Any questions for the speaker?
I have a remark. So first, I would never use CO2 capture to do and then it's oil recovery, because at the end you are going to extract oil, and it means that you will not have a positive effect on the carbon dioxide balance, right? So, but then I have a question concerning the comparison between those systems and then the adsorption systems, or the use of more conventional way of capturing carbon dioxide, like MEA, for example. Do you have an idea of how it compares?
Yeah, I don't have the comparison with the conventional, such as MEA or MDA, okay, or absorption. I believe that using cryogenic distillation or CFC can also control the CO2 emission.
Yeah, but here the energy that you consume is electricity. Yeah. Then it compares to others that are consuming heat. So which is different for the overall integration, for the systemic integration of the system.
Yeah.
But if you do not have the numbers, then
Sorry.
Other questions? So I have one question. I may have missed it. What are the temperatures you're looking at?
The temperature is about minus 50 degrees Celsius.
Okay.
With operation.
Okay. And you showed one picture where you have a column where the middle zone is freeze zone.
Right.
So just from an equipment design standpoint, I'm wondering how do you actually achieve that, these transitions?
I don't know in industry whether they have implemented or not.
Okay.
You can see that that's only the recent works by some researchers.
Because typically you have a column where you have one-way temperature change, distillation column. Now you have a central zone which is freeze zone, but on top and bottom you have higher temperatures. I'm just wondering how that is enabled in the column.
I think that's something like this. Well, you have the top column. Of course, this is going to be the lower temperature, right? And this is going to be the high temperature. And in this, we use a flash for simulation.
Okay.
It's just like in the conventional distillation column. You also have at every stage it's a flash operation. So,
Any final questions for the speaker? If not, let's thank the speaker.